Now in this lecture we'll answer on two questions. In the first question we'll find out the radius of this circle that is inscribed by the right triangle ABC. In the second question we'll find out the area of the blue right triangle that is inscribed by the quarter circle. So we'll start with the first question. In the drawing we have the right triangle ABC, side AB equals to 8 units, angle ABC equals to 90 degrees. Inside this right triangle ABC we have this circle that is inscribed by the triangle, and we want to find out the radius of this circle that is inscribed by the triangle. So first of all we will define side, and we also know it is given us the question that side BC and side AC, the lengths of side BC and side AC are integers. And we want to find out the radius of this circle that is inscribed by triangle ABC. So first of all we will define side BC as A. Side BC equals to A units according to our definition, and we define side AC, that is the hypotenuse of the right triangle ABC, as B. Okay. In the next step, we will implement the Pythagoras theorem for the right triangle ABC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the square of the perpendiculars. Here by PT is the relation for Pythagoras theorem. The square of the hypotenuse is AC squared. And it is equal to the sum of the square of the perpendiculars, that is to say it is equal to AB squared plus BC squared. I'll repeat again. In the right triangle ABC, according to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. AC equals to B according to our definition, so AC squared will be equal to B squared, that is equal to AB squared. AB equals to 8 units, so AB squared equals to 8 squared, that is 64, plus BC squared. BC equals to A according to our definition, therefore BC squared is A squared. So in conclusion, we found out that according to equation number 1, B squared equals to 64 plus A squared. Here we subtract A squared from this equation number 1, and we get that according to equation number 1, B squared minus A squared equals to 64. So here we will use the algebraic identity that states that B squared minus A squared equals to B plus A times B minus A, and it is equal to 64 according to equation number 1. So here we know that A, C and BC are integers. AC equals to B and BC equals to A. That is to say, A and B are integers according to what is given as the question. This is the first thing that we know. And the second thing is that A and B are the lengths of the right triangle ABC. So A and B are lengths, and as lengths they must be a positive number. It must be positive. So from 1 and 2 we will derive that A and B are positive integers. That is to say, they are the natural numbers. A and B are positive integers. And because of the fact that A and B are positive integers, we get that A plus B or B plus A must be greater than B minus A. Why? Because when you add two positive integers to each other, the result must be greater than the case that when you subtract them from each other. Okay? And we also know that, so B is positive integer and A is positive integer, so B plus A is also a positive integer. When you add two positive integers to each other, the result must be a positive integer. And we also know that the hypotenuse B is always will be greater than the perpendicular A, so B is greater than A. We subtract A from this inequality and we get that B minus A is greater than 0. So B minus A is a positive number. B is a positive integer. A is a positive integer. Therefore, when we subtract A from B, we will get positive integer. If the result is positive, then it must be a positive integer. So B minus A, it is also a positive integer. So actually, according to equation number 1, we multiply two positive integers by each other, and the result is 64. Actually, there are not a lot of possibilities that when you multiply two positive integers by each other, it will give you the result of 64. So we write down all the possibilities of two positive integers that we multiply them by each other, and we'll get the result of 64. Okay. Actually, B plus A might be 1 and b minus a must be 64. 1 times 64 is 64. B plus a might be 2, and b minus a might be 32. 2 times 34, 2 times 32 is 64. B plus a might be 4, and b minus a might be 16. 4 times 16 is 64. B plus a might be 8, and b minus a might be also 8. 8 times 8 is also 64. B plus a might be 16, and b minus a might be 4, and b plus a must be 32, and b minus a might be 2, and finally b plus a might be 64, while b minus a must be 1. 64 times 1 is also 64. So we have here 7 possibilities for the values of b plus a and b minus a that we know that there are 2 positive integers. Okay, but because of the fact that we have already found out that b plus a is greater than b minus a, so b plus a are all the numbers in column 1, while b minus a are all the numbers in column 2. And according to this inequality, the first column must be greater than the second column. Okay, so we check which options give us that the first column is greater than the second column. Here, one that is in the first column is not greater than 64, therefore this possibility is incorrect possibility. We'll cancel this solution. 2 is not greater than 32, this option is not good option. 4 is not greater than 16, so this option is not good option. 8 is not greater than 8, so this option is also not a good option. 16 is greater than 4, therefore this option is a good option. 32 is also greater than 2, this option is also a good option. And finally 64 is also greater than 1, so this is a good option. So we have 3 possibilities for the solution to the question. In the next step, we will add the 2 numbers together in order to find out what the result, and from the result we will learn more about the possibilities that we have. So b plus a plus b minus a, it is equal to b plus b, that is 2b, and a minus a is 0. So in conclusion, when we add the 2 numbers together, we will get 2b. b is a positive integer, therefore 2b must be an even number. Even number. Okay. So when we add the first number to the second number, we must get an even number. Otherwise, this possibility is not a good possibility. So we'll check now which options will give us an even number when we add the 2 numbers together. 16 plus 4 is 20, and 20 is an even number, so this is a good possibility. 32 plus 2 is 34, so 34 is also an even number. That is to say this is a good possibility. 64 plus 1 is 65. 65 is not an even number, it is an odd number, so we cancel this option and we're left only with 2 solutions to the question, b plus a will be equal to 16 and b minus a equals to 4. And the second solution is that b plus a is 32 and b minus a is 2. So we write down the two solutions that are possible to the question. Actually, in the next step, we'll find out the values of a and b in each possibility. According to the first option, we know that b plus a equals to 16, while b minus a it is equals to 4. This is the first option. And according to the second option, we found out that b plus a equals to 32, while b minus a equals to 2. Okay. In the next step, we will we'll focus on the first solution, first option, and we'll add equation number 1 to equation number 2. We get that b plus b is 2b, a minus a is 0, so 26 equals to 16 plus 4 is 20. Found that out the 2b equals to 20, we divide this equation by 2, and we get that b equals to 20 over 2 is 10. b equals to 10 units. Now we'll find out the value of a according to this equation. b plus a equals to 16. We subtract b from this equation, and we get that a equals to 16 minus b. So a equals to 16 minus b, and b equals to 10. So it is 16 minus 10. 16 minus 10 is 6. So in conclusion, we found out that a, that is the perpendicular, equals to 6 units, and b, that is the hypotenuse of the right triangle, equals to 10 units. This is the first option. And according to the second solution, here we will add the two equations together. b plus b is 2b. A minus a is 0. In the other side of the equation we have 32 plus 2 is 34. So here we divide this equation by 2, and we get that b equals to 34 over 2 is 17. So the hypotenuse b of the right triangle ABC equals to 17 units. And a, according to this equation, b plus a equals to 32. We'll subtract b from this equation, and we get that a equals to 32 minus b. So actually here a equals to 32 minus b, and b is 17, so we substitute b by 17. 32 minus 17 is 15. So in conclusion, we found out that according to the second option, a, the perpendicular a equals to 15 units, and the hypotenuse a of the right triangle ABC equals to 17 units. Now I will draw the two right triangles in here. According to the first option, we have a right triangle ABC. In the right triangle ABC, It has given us the question that AB equals to 8 units. We just right now found out that BC equals to 6 units and the hypotenuse AC equals to 10 units. In this right triangle ABC, we have a circle that is inscribed in this right triangle. This is the circle that is inscribed by this right triangle ABC, and we are looking for the radius of this circle that is inscribed by triangle ABC. So we define the radius of this circle as capital R. Now we have to find out the value of capital R. This is according to the first solution, and according to the second option, we have another right triangle ABC. It is given us the question that side AB equals to 8 units, BC equals to 15 units, and the hypotenuse equals to 17 units. Inside this right triangle ABC, we have a circle that is described by the right triangle. And we are actually looking for the radius of this circle that is described by the right triangle. So we define the radius of this circle as capital R. So we actually have to find out the radii of the two right triangles. In order to find out the radii of the two right triangles in these two specific, we have to find out the radii of the two circles that are described in the right triangles. In order to find out the radii of the two circles that are described by those specific right triangles, we will actually take a right triangle that could be any right triangle. Inside this right triangle, we have this circle, and we will find out the radius of this circle. So we will get a formula that is true for any right triangle, and we'll use the new formula for our two right specific triangles. So this is triangle ABC that could be any right triangle. So we define side AB as A. Here, side AB equals to A units according to our definition. We will define side BC as B. Side BC equals to B units according to our definition. And we will define side AC as C. We will define the center of this circle as O. We will define the point of tendency of tangent BC with this circle as M. We will define the point of tendency of tangent AB with this circle as N. In the next step, we will join points O and then together by a straight line. O is the center of the circle, N is the point of the circle itself, therefore ON is the radius of this circle that is equal to capital R according to our definition. In the next step, I present to you rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have tangent we have this radius OM that is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then according to rule number 1, tangent AB will be perpendicular to the radius NO. So if AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we have here the radius OM that is drawn to the point of tendency. That is to say the radius OM it is drawn to point M, that is the point of tendency of tangent BC with this circle. Whenever a radius that is drawn to the point of tendency, then according to rule number 1, tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So here we found out that in quadrilateral NOBM we have 1, 2, 3 right angles. Again, in quadrilateral NOBM we have 1, 2, 3 right angles. And the sum of the right angles is 90 times 3 is 470 degrees. Plus the size of the fourth angle that is actually angle NOM. In total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. If we subtract 270 degrees from the equation, we get that the missing angle NOM, this angle, it is equal to 90 degrees, it is a right angle. So actually in quadrilateral NOBM, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral NOBM as a rectangle. But we know that the opposite sides of a rectangle are equal to each other. That is to say, NO equals to BM. But we have already found out that NO equals to R. Therefore, BM that is equal to NO must be also equal to capital R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that NB equals to OM. But we have already found out that OM equals to R. And NB that is equals to OM must be also equal to R. And B equals to capital R. So we actually found out that quadrilateral NOBM, it is not a rectangle but a square because of the fact that all of its sides are equal to each other, they are equal to capital R. In the next step we'll find out the length of line segment AN. Here AN equals to AB minus BN. AN equals to AB minus BN. AB is A minus BN. BN is R. So in conclusion we found out that AN equals to A minus R. Likewise, we find out the length of line segment MC from the drawing. It is very easy to see that MC equals to BC minus BM. BC is B and BM is R, therefore BC minus BM is B minus R. So in conclusion, we found out that MC equals to B minus R, and here AN equals to A minus R. In the next step, I present to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Again, the lengths of two tangents from a common external point to a circle are equal. So if we focus on the common external point, point A, from the common external point, point A, we have two tangents to this circle, tangent AN, and here we define the point of tendency of tangent AC with this circle as N. So the second tangent from point A to this circle is tangent AN. So we have tangent AN and tangent AN from point A. And according to rule number 2, they must be equal to each other. That is to say, AN must be equal to AN. But we already found out that AN equals to A minus R. Therefore, AN must be also equal to A minus R. Okay. Likewise, in the next step, we focus on the current standpoint point C. From the current standpoint point C, we have two tangents to this circle. Tendency M and tendency L, and according to rule number 2, they are equal to each other. That is to say, Cm equals to Cl. But Cm equals to B minus 4, therefore Cl that is equal to Cm must be also equal to B minus 4. Okay? B minus R. Here, Cl equals to Cm, and Cm equals to B minus R, therefore Cl will be also equal to B minus R. Okay, so in conclusion, we found out that Cl equals to B minus R and Al equals to A minus R. And what is the length of the hypotenuse AC? The hypotenuse AC will be equal to AC equals to AL plus LC. AL plus LC equals to AC. Yeah. AL equals to AL. AC equals to AL plus LC. According to our definition, AC equals to C, so we substitute AC by C. And it is equal to AL. AL equals to A minus R. So we substitute AL by A minus R. Plus LC. Yeah, LC equals to B minus R, so we substitute LC by B minus R. So in conclusion, we found out that C equals to A minus R plus B minus R. That is to say, C equals to A plus B minus R plus minus R is minus 2R. Okay, here we will add we will add 2R to this equation, and we'll get that 2R plus C equals to A plus B. Here we subtract C from this equation, and we get that according to this equation, 2R equals to A plus B minus C. Here we divide this equation by 2, and we get that R equals to A plus B minus C over 2. So we found out the general formula to find out the radius of a circle that is described by a right triangle. Now we can use this new formula in order to find out the radii of the two triangles that we have here. According to the formula, the radius of those two circles will be equal to A plus B minus C over 2. A plus B is the sum of their perpendiculars, while C is the hypotenuse. So the radius of this circle will be equal to the sum of its perpendiculars, that is 8 plus 6, that is 14, minus the hypotenuse, that is 10 over 2. 14 minus 10 is 4, and 4 over 2 is 2. So we found out that the radius of this circle that is described by this triangle ABC, is equal to 2 units. We have also a second solution. Here, according to this solution, the second option, the radius of this circle that is described by this right triangle ABC will be equal to the sum of its perpendiculars, that is to say 8 plus 15 is 23, minus the hypotenuse, that is 17 over 2. 23 minus 17 is 6, and 6 over 2 is 3. So, according to the second solution, the radius of the circle that is described by the right angle triangle ABC equals to 3 units. So we actually found out two solutions to the question. The radius of this circle that is described by this specific right triangle ABC could be equal to either 2 units or 3 units. So here, the answer to the question is that the radius that is inscribed by the right triangle ABC could be equal to either to 2 units or to 3 units. So we finished with the first question. The next step I will present to you the second question, and we'll solve the second question in two different methods. Okay. In the drawing, we have a quarter circle. Side OB equals to 2 units. AD equals to DO. Inside this quarter circle, we have the right triangle DCB, and we want to find out the area of the blue right triangle DCB. Okay, first of all, because of the fact that AOB is a quarter circle, it means that angle AOB must be equal to 90 degrees. And it also means that point O is the center of the quarter circle, and also that OB is the radius of the quarter circle, and AO is also the radius of the quarter circle. So we write those things down. Here, AO equals to OB. Now, the radius of the quarter circle, repeat again, AO equals to OB, this is the radius of the quarter circle, that is equal to 2 units according to what is given as the question. But AO, according to the drawing, AO equals to AD plus DO. If we define AD as X, then DO will be also equal to X because of the fact that they are equal to each other, so X plus X is 2X. So in conclusion, we got that 2X equals to 9, 2X equals to 2. Here we divide this equation by 2 and we get that X equals to 1. Here we found out that X equals to 1 unit. In the next step, we'll complete the quarter circle to a circle. And then we'll extend the radius OB by straight line until it touches the circle. And we'll define the touching point of the extended OB in the circle as point P. Point O is the center of the circle, point P is the point P is the point of the circle itself. That is exactly the definition of a radius. So PO is the radius of this circle that is equal to 2 units according to what is given as the question. Here we will extend the straight line CD by straight line until it touches the circle, and we define the touching point. Suppose that when we extend the straight line CD, it will fall here it will touch the circle at this point, point X. Point X is the touching point of the extended CD with this circle. So we actually created here angle BCX, that is a peripheral angle. You can write down that peripheral angle BCX is equal to 90 degrees, and it touches the circle at point X, that is obviously not point P. So we actually found out a peripheral angle that is equal to 90 degrees, and it is not resting on PB, that is the diameter of the circle. Why PB is the diameter? You can write down that PB is the diameter of the circle. Why PB is the diameter of the circle? Because of the fact that PB passes through point O, that is the center of the circle, and any chord that passes through the center of the circle must be the diameter of the circle. Therefore, PB is the diameter of the circle. Actually, we found out peripheral angle BCX that is equal to 90 degrees, and it is not resting on the diameter of the circle. That is a contradiction to the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. So, in order to avoid the contradiction, we must conclude that point X merges with point P, and in this way we get that the peripheral angle BCP that is equal to 90 degrees rests on the diameter of the circle, that is BP. Okay? Therefore, we know that when we extend CD by straight line, it must touch the circle at point P and only at point P. At point P and only at point P. That is to say, point X merges with point P. So, we found out that PB is the diameter of the circle, and we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the straight line PB, on the upper side of the straight line PB at point O, then the sum of the angles here must be equal to 180 degrees. So which angles we have in the upper side of PB at point O? We have here 90 degrees plus angle AOP. In total, they must be equal to 180 degrees. So in order to complete the sum of the angles to 180 degrees, this angle must be equal to 90 degrees. Okay? Here, 90 degrees plus 90 degrees is 180 degrees. Okay? Therefore, this angle must be equal to 90 degrees. Otherwise, at point O, the sum of the angles will not be equal to 180 degrees. Okay? So here, we will find out the area of the blue right triangle POD. We find out the diameter, the length of the diameter BO and the right triangle POD. The right triangle POD, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. By PT is the relation for Pythagoras theorem. So the square of the hypotenuse is PD square. and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to P all square plus OD square. Okay, plus OD square. I repeat again. In the right triangle POB, according to the Pythagoras theorem, PD square equals to PO square plus OD square. So PD square equals to PO square. PO is 2, so PO square is 2 squared, that is 4, plus OD square. OD is 1, so OD square is 1 squared, that is 1. So in conclusion, we found out that PD square equals to 4 plus 1. 4 plus 1 is 5. So we found out that PD square equals to 5. We take out of this equation and we find out that the hypotenuse PD of the right triangle POB equals to the square root of 5 units. So we can write here in the drawing that the length of the hypotenuse PD is equal to square root of 5 units. We repeat on the same process with the right triangle DOB. On the right triangle DOB according to the Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. So dB square will be equal to d all square plus OV square. Okay. So in the right triangle DOB, dB square equals to d square plus OB square. So dB square equals to dO square. dO is 1, so dO square is 1 square, that is 1. Plus OB square. OB is 2, so OB square is 2 square, that is 4. So in conclusion, we found out that dB square equals to 1 plus 4, that is 5. We take out all of this equation and we found out that the hypotenuse dB and the right triangle DOB equals to square root of 5 units. So I can write here that the hypotenuse dB equals to the square root of 5 units. In the next step, we will extend the radius AO by a straight line until it touches the circle. At point Z. Okay, so point O is the center of the circle, point Z is the point of the circle itself. This is a Grave-Reader definition of a radius. OZ is the radius of this circle that is equal to 2 units. In the next step, we will implement rule number 1 in our drawing. Rule number 1 talks about two chords that intersect with each other inside the circle. So we have here this circle. inside this circle we have called AB. This is called AB. That intersects with chord CD. This is called CD. It's point O. So if this is the data that has been given to us, then the following equation is true. That AO times OB equals to CO times OD. Again, chord AB intersects with chord CD at point O. Therefore, according to rule number 1, AO times OB equals to CO times OD. We can implement rule number 1 in our drawing, because in our drawing we have here chord AZ this chord intersects with chord CP at point D. Point D is the intersection point of chord AZ with chord CP. Again, chord AZ intersects with chord CP at point D. Chord AZ intersects with chord CP at point D. Therefore, according to rule number 1, we get that AD times DZ equals to CD equals to CD times DP. Okay, AD times DZ equals to CD times DP. Okay, AD equals to 1, DZ equals to 1 plus 2, that is 3, and it is equal to CD. CD is the missing 9 segment, so we leave it as it is, times DP. DP equals to the square root of 5 units. So in conclusion, we found out that 3 equals to square root of 5 times CD. We divide this equation by square root of 5, and we get that according to this equation, CD equals to 3 over square root of 5 units. Okay. So we found out here that CD equals to 3 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on this right blue triangle DCB. According to the Pythagoras theorem, in the right blue triangle DCB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, dB squared equals to DC square plus CB square. So I repeat again, in the right triangle triangle DCB, according to the Pythagoras theorem, DB square equals to DC square plus CB square. DB equals to square root of 5, so DB square is square root of 5 squared, that is 5. And it is equal to DC square. DC is the missing line segment, so we leave it as it is. DC square plus CB square. CB equals to 3 over square root of 5, so CB square is square root of 3 over square root of 5, so the square of 3 over 5 is 3 squared, that is 9, over square root of 5 squared, that is 5. So in conclusion, we found out that 5 equals to CD square, DC square plus 9/5. So we subtract 9/5 from this equation, and we get that 5 minus 9/5 equals to DC square. Here we multiply 5 by 5 and then we divide it by 5 in order to have a common factor with this expression. 5 times 5 is 25. Minus 9 over 5. That is equal to DC square okay. So DC equals to 25 minus 9 is 16, which is 16 over 5. This is equal actually to DC square. Here we take out of this equation and we get that the length of side CD of triangle DCB is equal actually to square root of 16, that is 4, over square root of 5. So you can write down in the drawing that this equals to 4 over square root of 5. Now it is very easy to find out the area of this right blue triangle, triangle DCB. The area of the blue right triangle, triangle DCB will be equal to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. I repeat again, the area of the blue right triangle, triangle DCB equals to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. So here DC equals to 3 over square root of 5, while CB equals to 4 over square root of 5, all divided by 2. So we shall find out that the area of the right blue triangle, triangle DCB, here we have 3 times 4 is 12, so in the numerator we have 12, over square root of 5 times square root of 5 is 5, times 2. So here 12 over 2 is 6, and in the numerator we left only with 5. So the area of the right blue triangle, triangle DCB equals to either 6 over 5 units, so in terms of numbers it is equal to 1.2 square units. We finished with the first method. In the next step I will present to you the second method. We have already found out in the first method that angle A or B equals to 90 degrees. AD equals to 1 unit. DO also equals to 1 unit. The center of the quarter circle is point O, the center, and the radius of this quarter circle is OB, that is equal to AO, that is equal to 2 units. In the next step, we'll complete the quarter circle to a semicircle. Here, we'll extend the radius BO until it touches the semicircle, At this point we define the touching point of the extended BO and the semicircle as point P. O is the center of the quarter circle and also the center of the semicircle. P is the point of the semicircle itself. This is exactly the definition of a radius. So PO is the radius of the quarter circle that is equal to 2 units. In the next step, we will extend side CD by a straight line until it touches the circle, and according to the first method, when we extend side CD by a straight line, it must touch the circle or the semicircle at point P and only at point P and not in any other point. So if we extend side CD by a straight line, it will touch the semicircle at point P according to the first method. We have already found out that angle DOP, this angle equals to 90 degrees, therefore DOP is the right triangle. We have already found out that in the first method that the hypotenuse DP equals to square root of 5 units. Likewise, we already found out that the hypotenuse in the right triangle DOB equals to also square root of 5 units. And we will define angle DPO as theta. We will focus on the right triangle DPO. Angle DPO equals to theta. Angle DOP equals to 90 degrees. So this angle, the third angle, must be equal to 90 degrees minus theta. In order to complete the sum of the angles in this right triangle to 180 degrees, this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. Okay? And here, if we focus on the right triangle BCP, this angle equals to theta, this angle equals to 90 degrees, so the missing angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in this right triangle PCB. So 180 degrees, this angle must be equal to 90 degrees minus theta. In the next step, we'll prove that the right triangle POD is similar to the right triangle PBC. So, I'll write it down. We'll prove that the right triangle PDO is similar to the right triangle PCB. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle POD, this angle equals to angle PCB, this angle, and they are both equal to 90 degrees, therefore they are equal to each other. I'll repeat again. Angle POD equals to angle BCB equals to 90 degrees. In addition, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle PDO equals to this angle, that is angle CBA, and they are both equal to 90 degrees minus theta, therefore they are equal to each other. I'll repeat again, angle PDO equals to angle CBA, and they are both equal to 90 degrees minus theta, therefore they are equal to each other. And finally, this angle is the common angle that belongs to both triangles, therefore this angle equals to itself. So we can write down that angle DPO equals to this angle to itself, that is actually angle CPB, that is equal to theta, so it is a common angle that belongs to both triangles. Repeat again. Angle BPO equals to angle CPB equals to theta. That is to say, this angle equals to itself, because it is a common angle that belongs to both triangles. So all three angles of triangle PDO can go into all three angles of triangle PCB. Therefore, triangle PDO is similar. This is the sign of similar to triangle PCB, according to angle similarity rule. Okay. And from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PD over PB equals to DO over CB, and it is equal to PO over PC. I'll repeat again, and we conclude that PD over PB equals to DO over CB equals to PO over PC. So here PD is square root of 5 units, PB is 2 plus 2, that is 4, and it is equal to DO is 1 over CB is the missing line segment, so we leave it as it is, and it is equal to PO is 2 over PC. PC equals to square root of 5 units plus DC. So in conclusion, found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. We create the first equation from this equality. This is the first equation. Square root of 5 over 4 equals to 1 over CB. Here we'll cross multiply this equation, equation number 1, and we'll get that according to equation number 1, square root of 5 times CB equals to 4. Here we'll divide this equation number 1 by square root of 5, and we'll get that according to equation number 1, CB equals to 4 over square root of 5 units. So we can write down in drawing that CB equals to 4 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle DCB. According to the Pythagoras theorem on the right blue triangle, triangle DCB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, dB square equals to DC square plus CB square. Okay. Repeat again. According to the Pythagoras theorem, on the right triangle DCB, the right blue triangle DCB, dB square equals to DC square plus CB square. dB is square root of 5, so dB square is square root of 5 square. That is 5. And it is equal to DC square. DC is the missing line segment, so we leave it as it is. DC square plus CB square. CB is 4 over square root of 5, so CB square is 16 over 5. So in conclusion, we found out that 5 equals to DC square minus 16 fifths. We subtract 16 fifths from this equation, and we get that 5 minus 16 fifths equals to DC square. Here we'll take, here I actually will multiply 5 by 5 and then we divide it by 5 in order to have a common factor over this expression. 5 times 5 is 25, so it is 25 minus 16 over 5, that is equal to dc square. 25 minus 16 is 9, so we have 9 over 5, that is equal to dc square. We take a root out of this equation and we get that the length of dc, it is equal actually to the square root of 9, that is 3, over square root of 5. So dc equals to 3 over square root of 5. Here you can write down that it is equal to 3 over square root of 5. Now it is very easy to find out the area of the blue right triangle, triangle DCB. It will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. I'm repeating again, the area of the blue right triangle, triangle DCB will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. DC equals to 3 over square root of 5, CB equals to 4 over square root of 5, all divided by 2. Okay. In the numerator we have 3 times 4, that is 12. In the denominator we have square root of 5 times square root of 5, that is 5, times 2. Here 12 over 2 is 6, so in the numerator we left only with 6, and in the denominator we left only with 5. So in conclusion, the area of the blue right triangle, triangle DCB, equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. We finished with the second method. In the next step I will summarize the lecture. We start with the first question. So here in the drawing we have the right triangle, triangle ABC. Side AB equals to 8 units and angle ABC equals to 90 degrees. We know that the length of side BC and the length of the hypotenuse AC are integers. Okay? And we want to find out, and beside this right triangle ABC we have this circle, and this circle is inscribed by the right triangle ABC, and we want to find out the radius of this circle. So first of all we define side BC as A and side AC, the hypotenuse as B. Then we implemented the Pythagoras theorem on the right triangle, triangle ABC. According to the Pythagoras theorem on the right triangle, triangle ABC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, AC square equals to AB square plus BC square. AC equals to B according to our definition, so AC square is B square. AB equals to 8, so AB square is 8 square, that is 64. BC equals to 8, so BC square is 8 square. So in conclusion, we found out that according to equation number 1, B square equals to 64 plus 8 square. We subtracted 8 square from this equation and we found out that B square minus 8 square equals to 64. Actually, the expression B square minus 8 square, according to the algebraic identity, B square minus A square equals to B plus A times B minus A, so we can substitute B square minus A square by B plus A times B minus A, and according to equation number 1, it is equal to 64. So here we know that here BC and AC are integers, and BC equals to A and AC equals to B. That is to say, A and B are integers, and because of the fact that A and B are the lengths of the right triangle, the length of sides of the right triangle, they must be positive numbers. So A and B is the length, they must be positive numbers. So from 1 and 2 we will conclude that a and b must be positive integers. Okay? And because of the fact that a and b are positive integers, it means that a plus b, or b plus 8 is the same, will be always greater than b minus a. Why? Because if you add two positive integers together, the result always will be greater than the case that you subtract the two integers from each other. Okay, so b plus a must be greater than b minus a because they are positive integers. This is one thing, but because of the fact that b is the hypotenuse is always greater than the other side. So b must be greater than a. Okay? We subtracted a from this inequality and we got that b minus a is greater than 0. That is to say, b minus a is a positive number. But because of the fact that b and a are positive integers, therefore, if b minus a is a positive number, it must be a positive integer. Okay? Because you are in the world of positive integers. If you add one positive integer to another, the result must be a positive integer. And the same thing is if you subtract one positive integer from another, it must be a positive integer. And if we know from the beginning that b minus a is a positive, therefore it means that b minus a must be a positive integer. So here, in conclusion, b plus a is a positive integer and b minus a is also a positive integer. So according to question number 1, we actually found out that if we multiply two positive integers by each other, the result will be equal to 64. So there are not a lot of possibilities for this equation. We have only a few possibilities that when we multiply two positive integers by each other, the result will give us 64. The first possibility is 1 and 64, the second is 2 and 32, the third is 4 and 16, the fifth is 8 and 8, the sixth is 16 and 4, and the seventh is 32 and 2, and the last one is 64 plus 1. Those are the only possibilities that the multiplication of two positive integers will give us 64. Okay, but because of the fact, so we have here 7 possibilities, but because of the fact that b plus a is greater than b minus a, it means that the first column must be greater than the second column, because b plus a is the first column and b minus a is the second column. Okay, so all the options, all the possibilities that will not give that the first column is greater than the second column will cancel those options. Here 1 is not greater than 64, so this option will get cancelled. 2 is not greater than 34, than 32, therefore this option will get cancelled. 4 is not greater than 16, so this option will also get cancelled. 8 is not greater than 8, therefore this option will also get cancelled. Here 16 is greater than 4, so this is a good option. 32 is greater than 2, this option is also a good option. And finally 64 is also greater than 1, that is to say this option is a good option. So in conclusion, we left only with 3 possibilities that are valid for our answer to the question. In the next step we will add the first number to the second number in order to find out the result of the adding the two numbers together. Here b plus a plus b minus a is b plus b is 2b and a minus a is 0. So we found out that if we add the two numbers together, the result is 2b, and 2b is an even number. So now we will add the two numbers together, and we will check whether if the result is an even number or not. If the result is not an even number, we'll cancel this option, because the result of adding the two numbers together must be an even number. b is a positive integer, and 2 times positive integer must be an even number. So here we have 16 plus 4 is 20, and 20 is an even number, so it is a good option. 32 plus 2 is 34, 34 is an even number, so it is a good option. While 61 plus 1 is 65, 65 is not an even number but an odd number, therefore we will cancel this option. So we left only with two solutions to the question, 16 and 4, and 32 and 2. So we write down the two solutions here. According to the first solution, b plus a is 16 and b minus a is 4. According to the second solution, to the second option, b plus a is 32 and b minus a is 2. We will focus on the first solution, first option, b plus a plus b minus a. We will add the two equations together. Here b plus a is 2b and a minus a is 0. In the other side of the equation we have 16 plus 4, that is 20. So in conclusion, we found out that 2b equals to 20. Here we divide this equation by 2 and we get that b equals to 10. So we found out that the hypotenuse b equals to 10 units. And we have also the equation that b plus a equals to 16. We subtract b from this equation and we find out that a equals to 16 minus b. And we have already found out that b equals to 10 units, so we can substitute b by 10 and we get that a equals to 16 minus b, that is 10. So 16 minus 10 is 6. So in conclusion, we found out that the perpendicular a in the right triangle ABC is equals to 6 units and the hypotenuse b equals to 10 units. And the other side is, it has given us in the question that is equal to 8 units. And according to the second option, b plus a is 32 and b minus a is 2. We added the two equations together, b plus b is 2b, a minus a is 0, and the other side of the equation we have 32 plus 2 is 34. So in conclusion, we found out that 2b equals to 34. We divided this equation by 2 and we get that b equals to 34 over 2 is 17. So the hypotenuse b equals to 17. According to this equation, b plus a equals to 32. We subtracted b from this equation and we found out that a equals to 32 minus b. But b equals to 17, so we can substitute b by 17, and we'll get that a equals to 13 minus b, that is 17. 13 minus 32 minus 17 is 15. So according to the second solution, a equals to 15, and b, the hypotenuse b equals to 17. So I drew the two right triangles here. According to the first solution, AB is given us that is equal to 8 units. The second perpendicular BC is equal to 6 units, and the hypotenuse AC equals to 10 units. Inside this right triangle, we have a circle that is described by the right triangle, and we want to find out the radius of this circle. According to the second option, AB equals to 8 units, BC equals to 15 units, and the hypotenuse AC equals to 17 units. Inside this right triangle, triangle ABC, we have this circle that is described by the right triangle, and we want to find out the radius of this circle. So in order to find out the radii of the two circles inside these right triangles, we will draw right triangle ABC. Here we have the right triangle ABC that could be any triangle. Inside this right triangle ABC, we have this circle. We will find out the radius of this circle, and we will use the new formula in order to find out the radii of the two circles here that are located inside the two right triangles. Why we can do it? because of the fact that here we took triangle ABC that could be any triangle. And especially triangle ABC could be those two right triangles, because it is good for all the triangles in the world. Therefore, it is also good for our two triangles. The new formula for the radius of this circle. So this is triangle ABC that could be any triangle. Side AB equals to A units, side BC equals to B units, and the hypotenuse AC equals to C units according to our definition. We define the center of this circle as O. We define the point of tendency of tangent AB with this circle as N. We define the point of tendency of tangent BC with this circle as M. Then we join points O and N together by a straight line. O is the center of the circle, N is the point of the circle itself. This is exactly the definition of a radius. That is to say, ON is the radius of this circle that is equal to capital R. We have rule number 1 that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have the radius ON that is drawn to the point of tendency. That is to say, it is drawn to point N, that is the point of tendency of tangent AB with this circle, and whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. So if AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, according to rule number 1, because of the fact that the radius OM, it is drawn to the point of tendency, and that is to say it is drawn to point M, that is the point of tendency of tangent BC with this circle. Therefore, according to rule number 1, the tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. So actually we found out that quadrilateral NOBM, we have 2 free right angles. And the sum of free right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is angle NOM. In total, the sum of those 4 angles must be equal to 360 degrees. So if we subtract from the equation 270 degrees, we'll get that the missing angle, this angle NOM, must be equal to 90 degrees. Okay? So we found out that in quadrilateral NOBM we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral NOBM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, NO equals to BM. NO equals to BM from one side, but we have already found out that NO equals to R. Therefore, BM also must be also equals to R. According to the same rule that the opposite sides of a rectangle are equal to each other, we get that MB equals to OM. But we have already found out that OM equals to R, so therefore NB must be also equal to R. So we found out that all the sides of quadrilateral NOBM are equal to each other, therefore quadrilateral NOBM is not a rectangle but a square. Then we found out the length of side line segment AN. From the drawing it is very easy to see that AN equals to AB minus NB. AB is A, NB is R, so AN equals to A minus R. Then we found out the length of line segment MC. Here MC equals to BC minus BN. BC is B and BM is R, so MC equals to B minus R. So in conclusion, we found out that MC equals to B minus R and AN equals to A minus R. Then I presented to you rule number 2 that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. We have here point A. From point A we have 2 tangents to the circle, tangent AN, tangent AL. And according to rule number 2 they are equal to each other. That is to say AN equals to AL. But AN equals to A minus R, therefore AL will be also equal to A minus R. Likewise, we focus on the common standpoint point C. From the common standpoint point C, we have 2 tangents to the circle, CM and tangent CL. And according to rule number 2, they are equal to each other. That is to say, CL equals to CM. But we have already found out that CM equals to B minus R, therefore CL must be also equal to B minus R. So in conclusion, we found out that CL equals to B minus R and AL equals to A minus R. And the length of the hypotenuse AC, it is equal to AL plus LC. AC equals to AL plus LC. AL equals to A minus R and LC equals to B minus R. So we substitute L by A minus R, and we substitute LC by B minus R, and we found out that C equals to A minus R plus B minus R. Here AC equals to C according to our definition, so we substitute AC by C. C equals to A minus R plus B minus R. That is to say, C equals to A plus B, minus R plus minus R is minus 2R. We added 2R to this equation and found out that 2R plus C equals to A plus B. We subtract C from this equation and found out that 2R equals to A plus B minus C. We divided this equation by 2 and found out that R equals to A minus B, R equals to A plus B minus C over 2. So we found out the general equation for any right triangle that blocks a circle, and the radius of a circle that is inscribed by a right triangle equals to R equals to A plus B minus C over 2. We'll use this formula in order to find out the radii of the two right triangles that blocks two circles. And here R equals to A plus B minus C over 2, that is to say it is equal to the sum of its perpendiculars minus the hypotenuse over 2. In these right triangles, the sum of its perpendiculars is 8 plus 6, that is 14, minus the hypotenuse, that is 10. 14 minus 10 is 4, and 4 over 2 is 2. So we found out that the radius of this circle that is described by triangle ABC equals to 2 units. And according to the second option, we have used this formula that R equals to 8 plus 15 minus the hypotenuse, that is 17 over 2. 8 plus 15 is 23. 23 minus 17 is 6. And 6 over 2 is 3. So, in conclusion, we found out that we have two answers to this question. The radius of this circle that is inscribed by the right triangle ABC will be equal to either 2 units or 3 units. We finished with the first question. Then I presented to you the second question, and we solved the second question in two different methods. In the drawing, we have a quarter circle. Side BO equals to 2 units, AD equals to DO. Inside this quarter circle, we have the right block triangle BCD, angle BCD equals to 90 degrees, and we want to find out the area of this right blue triangle BCD. So first of all, because of the fact that it's a quarter circle, this angle must be equal to 90 degrees. BO, that is 2 units, equals to the radius of the quarter circle, and we know that AD equals to DO, so therefore AO equals to AD plus DO. Here, AD equals to DO, AO equals to AD plus DO. It is clear from the drawing. So if AD equals to X, then DO must be also equal to X, because they are equal to each other. So AD is X and DO is X, so AD plus DO is X plus X, that is 2X. And according to what is given as the question, it is the radius of the circle that is equal to 2 units. So from this long equation, we derived that 2x equals to 2. We divided this equation by 2 and we found out that x equals to 1. So here, AD that is equal to x equals to 1, and DO that is also equals to x equals to 1. Then we completed the quarter circle to a circle. We extended the radius PO by straight line until it touches the circle at point P. Point P is the touching point of the extended PO in the circle. And here we extended side CD by a straight line, and we actually don't know where it touches the circle, and we assumed that the extended CD touches the circle at point X. Okay, so we actually created here peripheral angle BCX that is equal to 90 degrees. Here we know that PB, line segment PB, is the diameter of the circle. Why? Because it passes through the center of the circle, that is point O. Actually, line segment PB is a straight line. Why? Because we extended the radius BO by a straight line. And when you extend the straight line by a straight line, the result must be a straight line. So PB, it is a straight line, and it passes through point O, that is the center of the circle. Therefore, PB is the diameter of the circle. And we have here peripheral angle BCX that is equal to 90 degrees, and it doesn't rest on the diameter of the circle, that is PB. It rests on BX, that is not the diameter of the circle. And it is a contradiction, because any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle, that is PB. So to avoid this contradiction, we must conclude that point X merges with point P, and here we will have the peripheral angle BCP that is equal to 90 degrees, and this peripheral angle BCP indeed rests on the diameter of the circle, that is BP. This is the way to avoid the contradiction that we have here. Peripheral angle BCP, so when we extend side CD by a straight line, it must touch the circle at point P and only at point P. Okay, and here we know that PB is the diameter is a straight line, and we know that the sum of the angles from one side of the straight line equals to 180 degrees. So if we focus on the upper side of the straight line PB at point O, then the sum of the angles here must be equal to 180 degrees. This angle equals to 90 degrees. This is the missing angle. The sum of those two angles must be equal to 180 degrees. So this angle must be also equal to 90 degrees in order to complete the sum of the angles on the upper side of BP at point O to 180 degrees. This angle must be equal to 90 degrees. Okay, so we have here right triangle, triangle POD. We implemented the Pythagoras theorem on the right triangle, triangle POD. According to the Pythagoras theorem, PD square equals to PO square plus OD square. PD square equals to PO square plus OD square. So PD square equals to PO square. PO equals to 2, so PO square is 2 square, that is 4, plus DO square. DO is 1, so DO square is 1 square, that is 1. So in conclusion, if I know that PD square equals to 4 plus 1 is 5, we took out of this equation and found out that the hypotenuse PD equals to the square root of 5 units. We implemented the Pythagoras theorem on the right triangle, triangle DOB, in order to find out that the hypotenuse DB. According to the Pythagoras theorem, DB square equals to DO square plus OB square. DB square equals to DO square plus OB square. So DB square equals to OD square. OD is 1, so OD square is 1 square, that is 1. Plus OB square. OB is 2, so OB square is 2 square, that is 2. So in conclusion, found out that DB square equals to 1 plus 4, that is 5. We took out of this equation and found out that DB equals to the square root of 5 units. Here, DB equals to the square root of 5 units. Okay, then we extended the radius AO by a straight line until it touches the circle at point Z. Okay, so here point O is the center of the circle, point Z is the point of the circle itself. This is exactly the definition. OZ is the radius. This is exactly the definition of the radius. So OZ is the radius of the circle, that is equal to 2 units according to what is given as the question. Then we implemented rule number 1 in our drawing. According to rule number 1, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay? In our drawing, we have chord AZ that intersects with chord CP at point D. Again, chord AZ intersects with chord CP at point D. Therefore, repeat again, chord AZ intersects with chord CP at point D. Therefore, according to rule number 1, we get that AD times DZ equals to CD times DP. Again, AD times DZ equals to CD times DP. AD is 1, DZ is 1 plus 2, that is 3, and CD is the missing line segment. DP is square root of 5 units. So in conclusion, we found out that 3 equals to square root of 5 units times CD. We divided this equation by square root of 5 units, and we found out that CD equals to 3 over square root of 5 units. Okay, then we implemented the Pythagoras theorem on the right blue triangle, triangle CDB. The square of the hypotenuse equals to the sum of the circles of the perpendiculars. That is to say, DB square equals to DC square plus CB square. Here, DB square equals to DC square plus CB square. DB is square root of 5 units, so DB square is square root of 5 squared, that is 5. DC square this is the missing 9 7, so we leave it as it is. CB is 4 over square root of 5, so CB square is 16 over 5. So in conclusion, we found out here, no, it's actually DC square. Here it is DC square. DC square is 3 over square root of 5 plus CB square. CB is 4 over square root of 5. CB is 4 over square root of 5. Actually, here we already found out that DC is 3 over square root of 5, and the missing side is CB. So here DB square equals to DC square plus CB square. So DC is 3 over square root of 5, therefore DC square is 9 over square root of 5. DC square is 9 over square root of 5. And the missing side here is CB. Okay, the missing side is CB. CB. Here it is CB. So actually, here we found out that 5 minus 9 over 5 equals to CB square. CB is the missing side. Then we multiplied 5 by 5 and then we divided by 5, and we got that 25 minus 9 equals to CB square. 25 minus 9 is 16. So this is square. So actually CB square equals to 16 over 5. We took out from this equation and we found out that CB equals to the square root of 16, that is 4 over square root of 5. So CB equals to 4 over square root of 5. Then it is very easy to find out the area of this right triangle, triangle DCB. It is the base, that is DC, times the I to the base, that is CB, over 2. The area of this right triangle, it is DC, that is the base, times the I to the base, that is CB, over 2. DC is 3 over square root of 5 units, CB is 4 over square root of 5 units, all divided by 2. Here 3 times 4 is 12, and square root of 5 over square root of 5 is 5, times 2. 12 over 2 is 6, and the denominator we left only with 5. So we found out that the area of the blue right triangle, triangle DCB, equals to either 6 over 5 units, or in terms of numbers, it is equal to 1.2 square units. We finished with the first method. Then I presented to you how to find out the area of the right blue triangle, triangle DCB, according to the second method. Here we have already found out in the first method that AD equals to 1 unit, DO equals also to 1 unit, and here we completed the quarter circle to a semicircle, then we extended line segment VO by a straight line until it touches the circle at point P. Point O is the center, point P is the point on the circle itself, therefore OP is the radius of this semicircle that is equal to 2 units. Then we extended side CD by a straight line until it touches the circle, and according to rule number 1, according to the first method, when you extend the side CD by a straight line, it must start the circle or the semicircle at point P and only at point P. According to the rule number 1, according to the first method, this angle equals to 90 degrees. We define this angle as theta. So this angle equals to theta. This angle equals to 90 degrees. This angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in this right triangle to 180 degrees. This angle must be equal to 90 degrees minus theta. If you focus on the right triangle CBP, this angle equals to theta. This angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta for the same reason. Then we proved that the right triangle PDO is similar to the right triangle PCB, the right big triangle PCB. Why those two right triangles are similar to each other? First of all, those two angles are both right angles, therefore they are equal to each other. Those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. And finally, this angle is a common angle that belongs to both triangles, so this angle equals to itself. So we actually prove that all the angles of triangle PCB can go to the angles of triangle POD. Therefore, triangle PCB is similar to triangle POD according to angle similarity rule. Okay, angle POD is similar to triangle PCB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we will conclude that PD over PB equals to DO over CB, and it is equal also to PO over PC. Again, DP over PB, PD over PB equals to DO over CB equals to PO over PC. Okay? So here PD equals to square root of 5 units, PB equals to PB equals to 2 plus 2, that is 4. DO equals to 1, CB is the missing line segment. PO equals to 2, and PC equals to square root of 5 plus DC. PC equals to square root of 5 plus DC. We derive the first equation from this long equation. For square root of 5 over 4 equals to 1 over CB. We of multiply this equation, and we found out that square root of 5 times CB equals to 4. We divided this equation by square root of 5, and we found out that CB equals to 4 over square root of 5 units. Then we implemented the Pythagoras theorem on this right blue triangle DCB in order to find out the side DC. According to the Pythagoras theorem on the right triangle DCB, dB square equals to DC square plus CB square. dB is square root of 5, so dB square is square root of 5 squared, that is 5. DC is the missing line segment, so we leave it as it is. CB is 4 over square root of 5, so CB square is 4 over square root of 5 square. 4 square is 16, and square root of 5 square is 5. So in conclusion, we found out that 5 equals to DC square plus 16 fifths. We subtracted 16 fifths from this equation and found out that DC square equals to 5 minus 16 fifths. We multiplied 5 by 5, and then we divided it by 5 in order to overcome a factor with this expression. So 5 times 5 is 25, and we have here 25 minus 16 over 5. 25 minus 16 is 9, so in this side of the equation we have 9 over 5. that is equal to DC squared. We took out of this equation and found out that the missing 9797 DC equals to the square root of 9, that is 3 over square root of 5. So DC here equals to 3 over square root of 5. Then the area of this right blue triangle, triangle DCB, is very simple to find out. It is equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. So it is the base DC times the height to the base, that is CB, over 2. DC is 3 over square root of 5. CB is 4 over square root of 5, all divided by 2. Here 3 times 4 is 12. In the denominator we have square root of 5 times square root of 5 is 5, times 2. 12 over 2 is 6, so in the numerator we left only with 6, and in the denominator we have only 5. So in conclusion, the area of the right blue triangle, triangle DCB, equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. Okay, so in both methods we arrive to the same result. That is to say the area of the right blue triangle, triangle DCB, equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. Okay, thank you very much.